So today what I'd like to do is talk a little bit about liquid nitrogen. Liquid nitrogen is a fascinating substance, but nitrogen itself is really very common. Nitrogen is 78% of the Earth's atmosphere. The other 21% is oxygen, and the remaining 1% or so is mostly argon with a little bit of carbon dioxide and water vapor thrown in there. So the air that we're breathing right now is mostly nitrogen. So liquid nitrogen is just nitrogen that's been liquefied. Well, how do you make liquid nitrogen? Liquid nitrogen is made through a cyclic process of compression and removal of heat. So you can compress a gas by, say, using a bicycle pump. You can actually pump the gas and make it get more compacted. So the molecules are closer together and they'll tend to want to stick together. Except that they won't, because compression actually heats up a gas. So you have to remove the heat, say, like you would with a refrigerator or with an air conditioner. So you first compress it, remove the heat, compress it some more, remove the heat. After that, after a while, you'll get liquefied air. Liquefied air contains a lot of oxygen. It's 21% by volume as a gas. So you have to sort of let the oxygen boil out if you want just liquid nitrogen. Liquid oxygen boils at minus 183 degrees Celsius, so 13 degrees hotter than the boiling point of liquid nitrogen, minus 196 degrees Celsius. So you can, by what they call fractional distillation, remove the oxygen and have just nitrogen. So that's how it's made. Now it's stored in a Dewar flask. A Dewar flask is a flask that has a metal outer jacket and a glass inner jacket. The glass jacket on the inside is made of a special kind of glass which is very resistant to thermal expansion and contraction. Because it's exposed to very great extremes of temperature, if it were to expand when it warms, it might break. So a thermos, like from your lunchbox, would probably break if you put liquid nitrogen in it, either when you first put it in or when it warmed up again. So this is specially designed. It was originally invented by Mr. James Dewar, and the space in between the glass flask and the outer metal flask is filled with nothing. Really, it's a vacuum. It's been evacuated of all air, except maybe a few molecules that it's really hard to get rid of every last speck.
When exposed to liquid nitrogen, the air inside a balloon contracts quite a bit. If you left it completely submerged for long enough, you would actually be able to liquefy the air inside the balloon, which is a different process from the contraction when you decrease the temperature at constant pressure. The air in the balloon is not being let out. Instead, it is simply losing volume. This can be demonstrated when I pull the balloon out and allow the air inside to warm up again by being in contact with the counter. The balloon seems to inflate itself. It's merely the air inside regaining the volume it has at a higher temperature.
Alright, so I'm going to put some liquid nitrogen in this cup. And then what I'm going to do is I'm going to dunk a flower in the cup. Now flowers, like all living tissue, are made mostly of water. Let's get rid of some of this. Made mostly of water, so when you expose them to liquid nitrogen, the water freezes solid. And the water in living tissue is captured inside individual cells. So the cell membrane, oops, I'm crushing it all over the place. So if you would be so kind, smash that right here. Actually, you probably crumple it up with your fingers if you want. Right over this, if you would, please.
Oh.
It makes it very brittle. Yeah. Okay, so it's not like a nice soft flour. Now, as this warms up, it will become more supple again and not breakable. But it will be pretty much damaged. So if you've heard stories about people being frozen in liquid nitrogen to be reawakened at some later point in time when we have more technology that can like revive them, it's not going to happen because they are just going to be a mess. It's going to be pretty gross, in fact. Now, another thing you can do with liquid nitrogen, if I could have you exchange your goggles with my other assistant here, is you can freeze a marshmallow. Now, marshmallows normally are pretty squishy. If you took a hammer to a marshmallow, not much happens. Okay, so the first one I'm going to do, my assistant is just going to watch. we're going to compare an ordinary marshmallow to one that's been frozen with the hammer treatment. It's not quite the same anymore. It's a little bit more like those ones you get out of those cereals that have marshmallows in them. So let's try and freeze one and see how they taste after they're frozen. If that makes any difference. Get it good and frozen here. Now, hopefully what will happen when you eat it is if you breathe out through your mouth, try not to spit pieces of the marshmallow, which is very hard to avoid, you may find that you can breathe out some nice fog.
It's going to be cold.
It's going to be very cold. Let it warm up just a tad. There you go. You might want to grab it with your fingers to make sure it's... There you go. Pop that in. Take a bite. No fog. No luck there. But how is it?
Lucky Charms.
Yeah. Well, excellent.
So that's how they create it.
So we have marshmallow before liquid nitrogen, nice and squishy, and after, not so much. One for you. And one for you. Very nice. Fire breathing, marshmallow eating dragon. Alright, now there's other things we can do. You take a rubber ball and freeze it. That does some fun things. So we're gonna put this in there to sort of cool off. I'm going to put a racket ball in there because if we put this one in, it's because it's solid. There we go, light and frost effect. That's a nice view of that. If you put this one in there, it doesn't break. I've tried.
It breaks?
No, this one won't break because it's solid rubber. But this one, what I'm going to do is cool off the ball below its glass transition temperature. Elastic polymers have what's called a glass transition temperature, below which they act more like glass than like a glass polymer. There we go. Alright, now this is where we grab the gloves because you need to be protected from the cold. I'm hoping this is really very, very cold.
I think you're running out of time.
And so we're going to test the elasticity of this ball.
Oh my god!
It's a lot less elastic than it was.
It's like a golf ball.
So if we do this,
Why didn't you
we'll
work?
smash.
Can I see the ball? Can I see the ball?
It's still a little too cold to hold, but people who are interested can take one as a souvenir later. Yeah.
I called it a nut piece later.
And now for the moment you've all been waiting for. And there you have it.